everybody. Thank you for coming. Let's make a start. We have I think, all the examiners here. We have Professor Gharib, Professor Dabiri, and Professor Steve Brunton online. So this is the thesis defense of Tanner Harms. And I've been away long enough. I know this is supposed to be really short. It was very nice to actually introduce the candidate a little more than just saying the name. So Tanner, you've been here since 2019. 19, joined the group in 20. And so Tanner has perhaps an insatiable curiosity for all aspects of sort of science and how they pertain to fluid mechanics. And so he's gone on several trips into machine learning at various computer vision. And what he's going to present to you today is a sort of an amalgamation of some of those things, and hopefully a potentially very useful utility going forward. Tanner came to us from the University of Wyoming, where he had a master's degree. He suffered through a second master's degree, and this is the culmination of all that work. So over to you, Tanner.
Thank you so much for the kind introduction, Beverly. And thank you, everybody, for being here. It's just such a joy to me to see all of these familiar faces. You're my community. We'll talk more about that later. I'm very thankful for you. I also want to make a couple administrative acknowledgements. First of all, thank you, Jamie, so much for getting us into this room. I was in the other room earlier today, and it was like 85 degrees. So can you imagine all of us in a room that's 85 degrees? I'm glad we're here. I'm glad we're here. And the other thing is, thanks, Alejandro, for managing the Zoom. I just really appreciate that, as it takes a lot of stress off of my back. And with that, I think I'm going to begin. So today, obviously, I'm giving my thesis defense, and I'm talking about some of the work that I've done over the last 5 years or so. I've titled the thesis Chasing After the Wind. And I know that for many of us, as we go through our PhD process, it can feel like chasing after the wind. But I'm literally trying to chase after the wind, all right? I'm trying to develop a technology that can identify structures in a flow and follow them as they evolve in time. So specifically, we're looking at detection strategies for autonomous mobile flow field measurements, and we'll get into more of what that means momentarily. Now, I want to start, let me make sure that I can click through things. There we go. I want to start by looking at basically, what are we able to measure experimentally in fluid mechanics and a little bit in oceanography? This here is a scale. I'm presenting it in meters, all right? 1 meter in the middle. You got kilometers over here, millimeters over here. And when I'm trying to resolve flow fields, the technology today allows us to measure a lot of these different scales. For example, we can look at the flow around a zebrafish larva, which is on the order of millimeters. We can also perform measurements on the scale of meters around something like a cyclist. This is a full-scale model of an elite cyclist, and they perform flow field measurements around this. If I use very different technologies from the field of physical oceanography, I can get flow scales in the ocean. This is from NASA Scientific Visualization Studio. These are ocean eddies and currents colored by the temperature. And they do this through a technique called satellite altimetry. Now, this leaves a region around right here where it's difficult to measure flow fields to get a good resolution of different structures within them. And this is sort of where we want to push our technologies forward with the work that we're going through today. So let's say that we've got a flow we're trying to measure. This is some flow that we care about. We're trying to measure experimentally. I feel very fortunate that I can show on the screen here the von Karman vortex street at the institution where Theodore von Karman was the director. That's just a very fortunate thing for me, and I feel very, I'm very fortunate. Now, if I were to take an experiment of this, I'd like to put a box around the entire thing. I'd like to be able to look many diameters downstream and multiple diameters in either direction of the cylinder in the spanwise flow. But if this is something that's like a wind turbine, the size of a wind turbine, the best I'm going to be able to do is something like this. I'll only have a small window of the flow I'll be able to actually measure. And I could try and get around this by multiplying my measurement apparatus using many cameras and different things like that. Or I can try and sample the same area and then stitch it all together. But then I lose some of the unsteady effects that could be important to the flow. What we're going to propose in this case is something slightly different. Instead of looking at one area and keeping it fixed, we'd like to take a camera and find something important in the flow and follow it as it evolves in time. So we're calling this autonomous mobile flow measurements or autonomous mobile flow field measurements. And colloquially, I'm calling it chasing after the wind. Now, my job here is to try and come up with detection strategies that are amenable to this problem. And that's what we're going to talk about today. But before I get into more specifics about that, I want to give a little bit of some flow measurement background for those of us that are not digging in the trenches, so to speak, of fluid mechanics experimentation. So how are flow fields measured? This is a sample image over here of an experiment that we've conducted. I shouldn't say we've conducted. This was actually conducted by Maysam Shemai before I got here, and I analyzed the data later on. But this area here, this region of the flow that looks sort of like a starry sky, that's where we're actually measuring the fluid. All those dots are particles that we've illuminated using a high-powered laser. And we record the motion of those particles using a camera that's situated beneath the flow perpendicular to the plane of interest. We also need to apply some kind of calibration to this so that we can take our pixel space knowledge of the flow motion and turn it into physical coordinates. Now, the algorithms that we use to do this kind of analysis are typically syntactic. And what I mean by that is that they're based on the structure of the data rather than, say, the meaning of the data. This just means that I'm applying my algorithm basically to the entire image indiscriminately. I'm not selectively looking at portions of it while neglecting other portions. I'm just going to apply it to all of that. And I depend on having data that's amenable to the algorithm. The other thing I want to bring up here is that a lot of fluid mechanical analysis is Eulerian, which means that I'm looking at a fixed domain in space and watching the flow move through that. The alternative is a Lagrangian frame, and we'll talk more about that in a little bit. Now, for those of you that aren't in the basement actually taking measurements, I know some of you are doing that. This is kind of what it looks like to run an experiment. Right here, we have a laser that goes through a beam splitter and reflects off a mirror into the flow, the test section here, which is where we make our measurements. Once we have those measurements, we then need to apply some kind of algorithm to make sense of them. So one of the most common algorithms we use, and on my committee is a man who is credited with developing this algorithm, is particle image velocimetry. And the way this works is, let's say I've got a bunch of particles that we've observed in an image, and I can segment that into many boxes. Now I have our first image, and I know the time step between images, so I look at the second image, and I try and measure how far particles move within each box, and I can do that through something called cross-correlation. And so I get a displacement in space, I get a displacement in time, and I can compute velocities for each of these little boxes that I'm interested in. Now, there are some challenges associated with PIV in the context of autonomous mobile flow field measurements. The first one of these is that the conventional approaches do not really account for the motion of an observer. So let's say I'm like flying a drone around, trying to look at a flow field. It's going to give us different results. And this is easier to see with an example. So once again, we have our cylinder flow. Here's our cylinder. We're moving from left to right, and the coloring is based on the horizontal velocity. Red means it's fast, blue means it's slow. And I'm looking in this region here where I've simulated a bunch of numerical tracers, and I'm visualizing those as PIV particles over here. Hopefully you can see that okay. I'm going to play this as a video, and we'll see that if I have an arbitrary translation and rotation to the frame that I'm observing, and I'm not aware of that translation and rotation, I'm not aware of those dynamics, it might be difficult to interpret what kind of flow I'm looking at just from what I see in the experiment. This has implications for the things that we measure. If we're trying to measure our x velocity, that's horizontal, or y velocity vertically, or the vorticity, you can see that if I have a stationary observer, I measure something different than if I have a dynamic observer. So the second thing that's a problem using these traditional tools in the AM/FM context is that the analyses are not really suitable for computing gradients in complex images. Like I said, we try and make our images as suitable for the algorithms as possible. So let's say instead that I'm trying to measure in the Caltech turtle ponds, there's clearly a bunch of tracers here, but there's a lot of other complicating features. For example, there's varied lighting. There are feature-rich reflections. For example, these trees over here are going to they'll shimmer in the reflections, and that's going to be an artificial velocity that an algorithm like PIV would pick up on. There's parts of the flow that we want to automatically ignore, like the shore here. We also have various types of tracers. So there's bubbles and leaves and clusters of leaves and bubbles. And we want to be able to use all of them if they're the right kind of tracer. Finally, there might be something like our turtle friend here, which is not a tracer that we want to measure. It's acting independently of the rest of the flow. And so we need to be able to distinguish those. So these are problems, and I'm going to call them shorter names. We have the problem of relative motion. That's our first issue. And the problem of feature-rich images. And these are the type of things that as we develop methods, we need to come up with tools that address the challenges. Okay. So we've got a roadmap moving forwards here. And remember, we're trying to get to detection strategies for these type of autonomous measurements. And here's sort of a direction we're going forward. The first thing we're going to look at is LGR, and it's going to address relative observer motion. So Lagrangian gradient regression, LGR, is the tool that we've developed to try and overcome the relative motion problem. Remember, I said that there's another frame to consider fluids in, and that is that of Lagrangian frame. That's the Lagrangian frame. And if I'm going to make, sorry, let me first explain. The Lagrangian frame considers fluid motion from the perspective of the particle moving through space, rather than from a fixed domain in space watching the fluid move through the domain. Okay, and so if I want to make Lagrangian measurements, what I'm going to do is I'm going to find particles in my flow and watch them evolve. I'm going to get these trajectories that each particle develops, and I'm going to study the trajectories instead of the field of flow motion in the region I'm looking at. Now, this gives us the machinery to apply different types of analyses to our data. So we're going to start looking at the theory of Lagrangian coherent structures. And Lagrangian coherent structures use trajectories to identify key flow features. Here are some photos from the seminal review paper by George Haller. On the top here, we have a rip current where unfortunately the tracers are people, but it seems like the boats are there to pick them up, so that's good. We also have the Deepwater Horizon oil spill here. In this case, the tracers are continuous. It's oil on top of the water, not discrete particles. And then we have a similar situation with the Great Red Spot over here. Now, one of the things that makes LCS an attractive framework for us to work in is that the analyses in the field are typically objective. This means that when I compute them, they perform the same regardless of the frame that I'm looking at. So I could be spinning my camera, I could be translating it, but I'm still going to pick up on the same features in the flow using these analyses from Lagrangian coherent structures. Now, there's a specific mathematical definition for this, but I encourage you to look it up on your own time. Now, there are a variety of different approximation methods that we could use to identify Lagrangian coherent structures. I'm going to use a categorization that was done by Alshouse and Peacock in 2015, and that is between dense methods and sparse methods. So within dense methods, there are two predominant approaches. The first one I'm calling gradient-based approaches, but they could also be called geometric. These include, for those of you that are familiar, analyses like the FTLE or the LAVD. And then there's probabilistic approaches. And some advantages of these are that they're strictly based on dynamical systems interpretation of the flow. So the gradient-based methods are trying to find exact continuum properties, or they're trying to estimate continuum mechanical properties. The probabilistic methods approximates the Perrin-Frobenius transfer operator to perform its analyses. And so these are directly related to analyses that people commonly use in dynamical systems. And that gives us a good understanding and a lot of theory to talk about when we're looking at these different types of analyses. The problem with them is that they're computationally expensive. So if I want to run an analysis here, I may be using over 1 million particles on even something like a very simple flow like this double gyre, which we'll dive into more. So a lot of researchers have developed alternative methods like these sparse methods, which are typically based on some form of clustering. So they're data-driven approaches. The advantage of this is that I can use the methods directly on natural tracer information. So if I want to, for example, in this image down here on the far right, those are actual ocean drifters that I'm using to get structural information of the flow from. Here's another example from Professor Dabiri where sparsely distributed tracers are used to find meaningful features in the flow. The difference here is that they're not as strictly related to the specific dynamical constants that we're trying to identify in these other methods. And for our case, we would really like to look at these gradient-based approaches, which give us continuum mechanical things or properties which are related to things like the velocity gradient and other aerodynamic quantities. So let's go into a little bit of background about these gradient-based approaches. To start with, we have our space that we're considering. So this is what I'm calling the Euclidean space here. And in this first, on the left-hand side of the screen, we have our reference domain. And I'm indicating that it's a reference by the 0 here. It's like the initial condition. And then we're considering then at some future time, this observed space. And the relationship between both of these is this flow map operator F. And it's important to know that this is a continuous transformation. So to go from the reference to the observed space, there's a smooth transformation back. So it's one-to-one there. Also, we want to consider these trajectories. So X here, this is saying the position of particle X0 at time t, given the initial conditions T0 and X0. This is saying that that's the instance of that fluid element at that reference time, or at that observed time. And if I string those together over all times, I have a trajectory. Now, often what I'd like to do is measure something called the flow map Jacobian. And so let's say down here, I've got some particles which are proximal, but maybe not infinitesimally close together. If I give them enough time in the flow, eventually they're going to have this nonlinear deformation that's going to skew this regression or this, this gradient, which I attempt to compute. The flow map Jacobian is the spatial derivative of the deformation with respect to the initial conditions. And if I have this nonlinear effect, then I'm going to get bad results when I try and do that. However, these are continuous trajectories, as we've mentioned. So as I go back closer in time to my initial condition, I'm going to have something that's more elliptical like this, ellipsoidal, I should say. And this is going to be a linear deformation, at least in the short-term approximation. So we're going to keep this as something linear in time if it's very short. We're going to say that beyond that, nonlinearity starts to characterize the deformations, okay? And we want to avoid these nonlinearities in our computations. So we're going to just remove all that and focus strictly on this. So if I bring this up on the screen, we can have, we have our initial positions here at XTI, and I'm going to talk about these in sort of a matrix formulation. So let's say that our initial the trajectory we're analyzing is indicated by this large dot, and all the neighboring trajectories we're connecting by calculating the distance to them there. And we're storing all that information in a matrix. We want to look at those same particles relative to the trajectory at a future time. And so this gives us the transformation from XTI to XTI plus 1, and we want to characterize the operator that defines that transformation. So we can define that as a matrix equation down here on the bottom. And what this says is that I have my deformations at time I, and if I apply the operator df, this is the flow map Jacobian, to those deformations, I'll come up with, or to those distances, I'll come up with the updated distances, the deformed condition at time I plus 1. And we have to remember that this is a linear deformation if we have a small enough time step, okay? Now, let's figure out how to solve this operator df. First, I'm going to perform a Moore-Penrose pseudo-inverse, and that's going to give me this is basically a regression here that I'm doing. I'm regressing this operator using this equation, and we want to add a little bit more control over this. So we're going to put in a kernel weighting matrix. I'm illustrating that kernel weighting matrix from this cover over here, where at the center point, that's my 0 there, and it's got a full value. And if I go far away from that, the value of my the relative importance of that particle in my regression is diminished. And so I'm weighting particles based on this matrix K to choose which particles I want to emphasize in my regression. This can cause some numerical stability problems if I don't add in a regularizer. So I add a very small regularization constant here, gamma, to make sure that my computations don't crash. All right, so let's bring this up to the next slide and talk about what we can compute from this. The first thing that we want is our velocity gradients. So if we can compute our velocity gradients, then we can calculate things like vorticity and other aerodynamic quantities that give us important features that we care about in our flow. We can also use this equation here to compute deformation gradients over arbitrary periods of time. So remember, these are over small time steps. And if we multiply them together over a larger domain or a larger interval, then we can actually compute the arbitrary interval here. And I encourage you to go read the thesis if you want to know more details about these computations. Great. So now that we have addressed, sort of talked about the formulation of LGR, we now need to validate it a little bit. So that's what this next section is about. To do that, we're going to use a benchmark test case. This is the double gyre flow. It's analytically defined by the equations over here on the right. And we're using the parameters on the bottom here, which are commonly used in Lagrangian coherent structures literature. Now, there's a couple blobs of particles that I'm showing here. These start in the center of a vortex, which is indicated by these concentric rings of constant vorticity. This is, I should say, this is counterclockwise, positive vorticity, so it moves counterclockwise. And then it's mirrored on the right. And this line goes back and forth. And as you can see, as I play the video, the particles that started near the center of the domain get spread out all over the place. They fill up the entire domain rather quickly. And those particles that start inside the vortex sort of rotate around indefinitely. This is just interesting. I think it's worth talking about. But the first thing we really want to compute is some kind of measure of the velocity gradient. And to do that, we're going to look at the vorticity, which I've defined this way here. We're calculating it from the velocity gradient, which we've already computed using Lagrangian gradient regression. So down here on the bottom, in the bottom left is our analytical result defined directly from the equations. And over here on the right are different particle densities, which we've used to compute these quantities with Lagrangian gradient regression. And really the point that I want to show here is that, you know, for all of the densities shown, we're representing the analytical result relatively well. I could figure out where the vortices are and their relative strength very easily from even 100 particles in the flow. Now we want to extend this a little bit further, so we're going to compare it to PIV and Lagrangian particle tracking pipelines using synthetic images that we've generated from simulated particles in the double gyre flow. So I'll play these videos, and this is sort of what we're looking at here. On the left, we have 200 particles in the domain, and on the right, we've got 2,500 particles in the domain. And the way that we're going to perform these analyses, first of all, we're going to use PIV. This is using open PIV. I'm going to do a 2-pass algorithm with vector validation, and then once I have velocity fields, I will compute finite differences over here. Next, we want to work on Lagrangian particle tracking. So we're going to start with our images and then compute trajectories using the algorithm of Kelly and Ouellette from 2011. It's freely available on their website. And then from there, we'll have trajectories which you can calculate velocities from. And from those velocities, we'll interpolate to a grid. So we have velocity fields, and then we can compute finite differences, which gives us our gradients. Finally, we're going to look at LGR, which is our approach. And we're going to use the same trajectories that we computed from Kelly and Ouellette's algorithm here. The difference is we then go directly to regressing gradients. So we never compute Eulerian fields in this process before we get to gradients. We get gradients directly from particle distance or particle deformations. Okay. However, we do interpolate at the end so that we can compare our results one-to-one with PIV and Lagrangian particle tracking. Okay, so here we have the 3 pipelines side by side. Again, on the bottom left here is a baseline. And I'm indicating how many particles I've used in this first column, which I'm displaying the images here that we used to compute these. So we've got 100 particles all the way up to 2,500 particles. The first thing that I want to point out from PIV is that PIV performs the best when there's more particles. When there's more particles in the flow that I've observed, there's more signal in my algorithm. So it's easier for me to get good results here. But when there aren't that many particles, signal to noise is bad. So this is where I end up. I get noisy results with few particles in PIV and good results with more particles. Interestingly, Lagrangian particle tracking seems to be the opposite. And this is because of the structure of the algorithm. So in Lagrangian particle tracking, I need to be able to find those trajectories. And if there's lots of particles in the frame, then I'm going to misidentify trajectories, and there's going to be ghost particles and all sorts of things that can complicate my trajectory calculation, so that when I get my velocity fields, there's errors. And then when I compute the gradients, those errors are amplified. And that's why we have lots of particles. You see these splotches, and you see these splotches in the domain because of basically trajectory misidentification. Interestingly, Lagrangian gradient regression seems to kind of overcome this. It performs the best in the middle here, but there's less of that, those interpolation effects because we're not interpolating as often. So I think that that's the reason why we perform a little bit better in this case for using our algorithm, is because we're interpolating less and we have more particles to sort of smooth out our behavior with. There's some other advantages with this technique that we have. First of all, like I said, Lagrangian gradient regression is fully Lagrangian. I never have to compute Eulerian fields before I get my gradients. And so that means that I can store all of my gradient information without ever saving it onto a mesh or a grid. I can keep it along the particle track definitions. And so that can be very space efficient if I'm looking at large flows, especially in 3 dimensions. It's going to be very difficult for me to observe enough tracers so that I have more tracers in my domain than I have 3-dimensional grid points. Another advantage of this is that Lagrangian gradient regression is k nearest neighbors limited, which this is a well understood algorithm that can be done very quickly. However, Lagrangian particle tracking is interpolation limited, and interpolation can be done very quickly, but the algorithms that people tend to use to interpolate here are very expensive. Things like Vic plus or just radial basis function interpolation scale poorly with the number of particles in my domain to the point where it can become very expensive to compute those interpolations. All right, now we've covered sort of the PIV and the velocity gradient section of LGR. I want to look a little bit at computing the Jacobian using FTLE. So to do this, we're going to consider a common metric in Lagrangian Coherent Structures literature, which is the finite time Lyapunov exponent. And here it is defined. Essentially, what it's measuring is how much fluid stretches from that point in the flow over some observation interval, okay? This is our baseline. What we're looking for essentially are these red ridges which go through the domain. Essentially what those are telling us is that fluid that starts on one side of those ridges is going to be prevented from going to the other side of those ridges throughout the time of the interval. It's sort of an indication of how mixing occurs in a flow. All right, so when we compute this in a conventional sense, we can see that the results don't turn out very well, especially with few particles. When I'm only using 250 particles and applying a conventional approach, I really don't do a good job of representing anything in the flow. However, in our method, we're able to get representation of the ridges that we care about finding, even with sparsely defined particles. The next thing I want to talk about are integrated metrics. So Lagrangian gradient regression also allows us to compute these integrated metrics. Perhaps the most common of these is the Lagrangian average vorticity deviation, which is defined here. It's essentially measuring the amount of rotation of a particle along its trajectory over time. And what you see in the baseline case here is that you have 2 vortices, which we know, and they're sort of got their vortex cores are at the peaks of these, and they have boundaries, which we care about finding. Interestingly, these integrated metrics, especially Lagrangian average vorticity deviation, perform better under sparse conditions than even the FTLE does using Lagrangian gradient regression. With only 100 particles in the domain, we're able to find accurate representations of the vortices in the flow, and we could relatively easily pinpoint where the peaks are. So to summarize quickly what we've done with Lagrangian gradient regression, we have basically computed or come up with a framework that synthetically brings together 3 different types of measurements. We can compute velocity gradients, we can compute flow map Jacobians, and then we can do integrated metrics using the same set of equations, essentially with very little modification in between analyses. We've also seen that we can compute comparable gradients to the standard pipelines. I didn't, in my analysis of PIV and LPT, want to make any claims that LGR performs better than those. I just really want to emphasize that they perform comparably. And so LGR, a very different paradigm for measuring gradients, performs comparably well to the traditional approaches. We also have noted that our approach to LGR outperforms conventional methods for computing the velocity gradients. So if you want to use natural tracers to find things like FTLE ridges, the LGR may be helpful in doing so. Okay. So now we've talked a little bit about Lagrangian gradient regression. We need to address the next problem, which is how do we deal with feature-rich images? And that's where we're going to go from here. So STT, which I had in the other frame, I'm referring to as semantic tracer tracking. And what exactly is a semantic tracer? So we've seen this image already. And let's say we're going to look at a portion of that image. We're going to look at the turtle in this area around it. Let's say that we want to analyze the motion of these particles in the flow. These yellow leaves and bubbles, those are going to be a better representation of the flow, and we want to focus on those. However, we have something like our turtle in the flow, which is not something we want to focus on. However, both of these are by some definition, a tracer that we could follow, right? We want to selectively choose these. As a person, I can say that's a leaf and that's a turtle. Don't look at the turtles, only look at the leaves. So we want to develop algorithms that do this for us. So semantic tracers are commonly studied in the literature. One example where that might be the case is if I'm looking at the motion of the tracer itself. This is an image from a study by the Wilhelmus group at Brown, where they're looking at the motion of ice in the North Atlantic. We also might consider watching the motion of plastic particles in the ocean, or bubbles, or brine shrimp and krill. All these things are tracers that we may want to actually study the dynamics of as they move around. Another example of something we'd like to do is remotely study flows. So if I have a river somewhere that's hard to reach, and I'd like to know the flow rate of that river, it would be helpful for me if I could study that from cameras that are far away from me. I'd also like to be able to do the same thing in tidal basins. So these are both examples of studying flows remotely using only naturally available tracers, which would be semantically defined. There are challenges, of course, which include that tracer distributions vary. They can vary between cases, and they can vary within a case. We also know that the scene has complicating features like reflections and things that we've already looked at. And then finally, the tracers are typically sparse, and that's going to preclude structure identification methods that we might normally apply. So to go through this study, we're going to have a case flow that we'll look at. And I'm calling this an asymmetric split flow, but it's essentially a blunt trailing edge to a long plate where the flow on the top surface is slow and the flow on the bottom surface is fast. As they come to the trailing edge, you get interesting behavior. Right after the trailing edge, you'll have bluff body shedding, and this eventually transitions into a shear layer downstream. Here are the flow properties for anyone that's interested in those. We also are going to seed this with unconventional tracers. So we're going to, instead of using PAV particles, we're going to use birch wood that we're just going to sit on top of the water and watch as it flows. Finally, we're going to use accessible optics that are affordably acquired for maybe less than $1,000. You could potentially do this experiment with your phone. So here's an example of the footage. Again, we're looking down on top of the water. This is our plate, and these are the particles. You can see some of the structures forming in the wake of the plate there. But it's also clear that there's a lot of confounding features too, like the reflections, like the gaps in the particles. All these things make it difficult to apply the normal algorithms. So what we've done is we've come up with a modular framework to try and address these things. The first step involves detecting tracers using large vision models, similar to the things that find your face on your phone and are now segmenting people out and removing people from images and things like that. We're also then, once we've found our tracers, going to use some kind of tracer tracking technique. This could be Lagrangian particle tracking, or it could be more specifically from the world of machine vision. And then once we have our trajectories, we have everything we need to input into the Lagrangian gradient regression algorithm, which we've already analyzed. The model that we're using for detection is the mask RCNN model. It involves an identification step where it finds where particles are, and then it classifies them and puts a mask around them using subsequent neural networks. Essentially, this is a two-part step. So we have our backbone, and this backbone is a large model that's been trained by Google or Facebook, somebody with access to millions or billions of images and billions of masks. So we want to use all of the information that they've already trained on this model. When we do our training, we're going to freeze that pre-trained model, and we're going to go on top of it and train just what we call the head here. The only downside is that we need to collect some training data before we can compute these things. So to get our training data, we use something called the segment anything model. Here's a picture from Caltech. And if I apply segment anything to it, you can see that it finds these semantic masks within the image. We have built an app around this to identify particles that we care about in the flow. They could be the birchwood that we're looking at, or later I'll show you that they're particles on the surface of the pond. It doesn't matter. We get to define what they are. We just go in and find them in some images. In our case, we have 165 or so images with masks in them. Once we've trained the model, what we end up with is something that looks like this, where we're able to represent most of the tracers using our masks, although there are some misdetections here. Once we have applied our models and got detections, we then need to do some tracer tracking. To do this, we use a template matching approach. So the first step here is to find a detection and look in the region around it. Then in the next frame, we try and figure out where that particle is, and that gives us a displacement. If it's satisfies certain thresholds like acceleration and velocity, then we'll say that it's a legitimate tracer on the trajectory that we're looking at. We may end up with misdetections here. So this gray trajectory is the true trajectory, but let's say I've found these tracers and I found these ones. To connect them together, I can make a polynomial fit of one trajectory and compare it to the start of the next trajectory. If it satisfies the threshold, we'll keep it and we'll stitch them together. Next, we calibrate to get the information in world coordinates. And once we've done that, we have something like this. I like to joke that this is the patriotic spaghetti, but if it's red, it's starting above the plate. If it's blue, it's starting below the plate. And if it's white, I found it first behind the plate. And you can sort of see how tracers mix over time in our flow that we're looking at. To show you what structures look like in the flow, we apply it to, we calculate vorticity using Lagrangian gradient regression, and this is the outcome. So you can see the structures forming and moving downstream behind the plate. And we're only doing this using the deformation of tracers in this case and applying the algorithms that we've developed. Great. So semantic tracer tracking offers a variety of different opportunities for future studies. For example, we could study multiple classes simultaneously. I didn't do this in my testing, but we could have gone and looked at just the rods and just the spheres and just the large spheres and studied their motion independently, but using the same frames. We can also do study dynamical flows beyond fluids. So Professor Brunton keyed me onto this interesting problem of herding sheep viewed aerially. And so I've computed sheep vorticity here for those of you that are interested. The model is modular, or the framework is modular. So as models continue to develop, and they have already since I've started this project, we can easily add them in to improve our results. And then finally, the hardware requirements are very lenient. So eventually you could potentially put this onto a phone and, democratize fluid mechanical measurements, which could be fun. All right. So we've looked at semantic tracer tracking. We have a framework for analyzing data, and let's finally go to some applications. The first application we're going to study is the simultaneous examination of surface tracer and subsurface fluid dynamics. So here's the schematic for our experiment. Effectively, what we're doing is we're looking at tracers on the surface of the water and performing PIV directly beneath the surface of the water. We're using a quiescent tank here and manipulating the flow with our captive trajectory system in the NOAA lab that we're operating as a tow tank. So we basically have an airfoil on the end of our robot, and we move that airfoil around and create flows and study them. So the flow that we're looking at is an impulsively stopped airfoil at negative angle of attack, just like what I showed on the screen there. So we move it and then we stop it, and that develops a large starting vortex off the sharp trailing edge there that's leading in the flow in this case. And we're using these parameters in our study. For those that are interested in the dynamics, here they are shown on the screen. This is the position in blue. We impulsively start and then stop the airfoil and begin recording as soon as the airfoil stops. Here are some of the tracer conditions that we look at. We perform a control case with no surface tracers using 10 runs, and then we have all these different tracer conditions. These are just sample images from those runs that we've collected. We're only really going to look at these cases in our results, but it's still interesting to see all them side by side. Now, if we're going to perform PIV on data that looks like this, we need to remove the surface tracers so that we can get a good representation of the flow beneath the surface. This can be done using standard techniques from image analysis. The first thing that we're going to do is apply a geometric mask to get rid of our solid object in the flow. This is our airfoil. We just remove it with a mask. Next, what we do is sort of an advanced median subtraction. So for every pixel in the flow, I fit a polynomial based on the intensity around that pixel, and I subtract it. It still leaves a little bit of residue in the images of where the tracers are, and we can remove that by just doing a threshold subtraction. So if the value of the pixel is below a certain threshold, I just set it to 0. And what you can see, I hope you can see from where you're sitting, that this is basically a representation of only the PIV particles without the surface tracers in the flow. So if we want to look at this as a video, this is sort of what we're able to see. I'm showing vorticity in this case. You can see that the airfoil just stopped. And now we've got our vortex, our starting vortex, interacting with the airfoil and being ejected up to the top right of the screen. Quickly, it starts to dissipate, and the particles spread out where the vortex is dissipating to leave this void in the surface of the water here. This is the flow that we're going to be analyzing. It's most accurate, or it's most repeatable in short times. And so when we look at our data in the future, it's going to be for the short time right after the stop of the airfoil. We want to also consider the results of our semantic tracer tracking stages. So here are some example frames of detections that we've made with the masks shown in color. They're not perfect, but they're pretty good. And then from these, we're able to calculate trajectories. So this is from the beeswax case here. We're just calculating trajectories. These are sample trajectories longer than 200 samples long. Not all of the trajectories that we calculated, but it's long ones. From these, we can start computing things like vorticity. So this is the PIV ensemble average of all 33 runs that we conducted. And we're going to compare this with cases that we've seen from the surface. So here we have computed vorticity based on, we've actually interpolated from the particle locations here to the field, and we're looking at the vorticity based on these different conditions. If I want to compare the vorticity from the ensemble to these, I can plot on top of all these images a constant contour of the vorticity from the ensemble. So that looks like this. And one of the things that's important to notice here is that despite these being imperfect tracers on the surface of the water and this being PIV underneath the surface, we're still representing the vortices in roughly the same places. That's important for us to know, that the immediate subsurface flow represents what we're measuring from the particle motion on the surface. And if you want to see where the particles were that we did our measurements, I've just decided to plot those on top here. Those with the beeswax, the smallest tracers, fill more of the screen because the beeswax are so small, they seemingly fill in the gaps, so to speak, whereas these are more spread out because they're larger particles. Finally, I'm going to talk about our last application, which are field measurements taken in the Caltech turtle ponds right next door. So here's a schematic of that. If you're here watching today, you're roughly up here in the corner. So this is where we are. And if we're going to be looking at where I took the measurements, it was in this lower pool, sort of close to, or in the middle of the garden. I've already shown you images from this data set, so you kind of have an idea of what the data looks like. But if you want to see what the, oh, I should also mention, this is important, that we didn't add any tracers to the flow. We just really what happened was I was walking around campus one day and I noticed that there were a lot of leaves in the pool. And so I ran and grabbed all my equipment and came outside and set up and took an impromptu experiment, which has been very productive for me. Here's some of the training data that we collected from the images. Once again, the way I collect the training data in these studies is I just collect videos and then I take sample frames and then I extract training information from those frames. Now, if we perform the tracer tracking, we can get trajectories that look something like this. All right, so I'm showing basically the color here represents how far along in the flow it is. Yellow represents the end of the recording. Blue represents the beginning of the recording. And you can start to see the character of the flow here. But one more thing, the shape here is due to the perspective of the camera. I had to flatten it out because I was not able to observe from directly above the flow. And so that's why we have this trapezoidal shape. We can see in this sort of the character of the flow. We have this large bulk rotation up here in the top left corner of the image, but there's these other vortices that seem to become evident as well. For example, this large one here and one right next to the rock at the beginning of the flow, and this vortex over here. Looking at the trajectories is nice, but we'd also like to look at the fluid mechanical properties of the flow. So let's take a look first at the vorticity. Here we see that, yes, indeed, there is a large counterclockwise rotation occurring in the bulk of the flow here. Right next to that, driven by that motion and perhaps the stagnation point right up here, we have these other rotations occurring in this cavity, and those drive this smaller vortex down here in the cove. We can also look at finite time measurements here. So in this case, we are looking at finite time Lyapunov exponent. This is measured over 8 seconds. And you can see some of the character here, but to make it a little bit easier to observe, I'm just going to highlight some of the ridges underneath using artificial addition. So I just drew these lines in. And what you can see here is that the large values of the ridge kind of follow along what we expect on the trajectories here, separating the bulk flow from the cove flow. The ridges are less strong inside of that secondary flow here, but they're still somewhat visible. We can also calculate the Lagrangian average vorticity deviation and see where those vortices are occurring. Remember, this is calculating integrated rotation over time. And what this shows is that there are 4 vortices that are roughly present in the flow. All right, and so to end this section, I want to just play a video of the flow in action. I'm actually showing integrated vorticity here. So this is like LAVD, but the absolute value isn't part of this. So we have a sign associated with the rotation, and we can see the character of the flow sort of evolving in time. This is mostly for fun. So I could do more to process this and make it more of a, I guess something to make conclusions from more strictly. All right, so that kind of covers everything that I wanted to talk about. Let's summarize. So the first thing that we did is we talked about Lagrangian gradient regression. That gave us an answer to the relative observer motion problem. This taught us that there's a theory to estimate gradients from sparse data. We then tried to address the problem of feature-rich images. This taught us a general approach for measuring flow dynamics in complex scenes. And then finally, we took this and applied it to applications. The first application was a synchronous study of surface, tracer, and subsurface flows. And the final application was for field measurements of flow kinematics using natural tracers alone. There's plenty of directions for future work here. The first thing that we could do is we could continue to develop theory associated with LGR. There's a lot of testing that still needs to be done. Like I said, we looked at one case when we did our comparison with PIV and LPT. Many permutations of that study could be done and maybe should be done. We would also like to consider other metrics, and there could be physics-informed modifications that could help us improve our results in fluid flows. Next, we would like to consider the algorithms and improve those. So, like I said, the algorithms in the machine learning world are evolving at an astronomical pace. There's plenty of new tools that could be applied to these applications, and it would be interesting to see how our results are improved based on the advances that have already been made in other parts of computer science. We'd also like to improve our tracer tracking protocol here. We're using a relatively simple approach to tracer tracking. It's also kind of computationally expensive, but many other cheaper and more effective ways do exist. Finally, and this is my favorite part, is to apply to new applications. There's plenty of applications where this could be interesting and applied. For example, 3D flows, all of this would apply to a 3D flow, even though in this case, we applied it only to planar flows. Next, we'd like to perform additional field measurements. This could be done from the side of the pool like I've done, or it could be done using a drone above a river or something. I think both would be interesting. And then it'd be fun to continue studying unconventional tracers as well and other aspects of dynamical systems literature. So we set out in this project to try and come up with a strategy to autonomously measure fluid flows. We haven't got there yet. But I think that the things that we've discovered along the way, while being meritorious in their own right, do provide a framework and a foundation for future autonomous measurements of flows. And I think that if computer scientists and the right people are given the tools to go there, we'll be able to chase after the wind and measure it. So thank you all very much. I'm now going to, I would normally